Chapter 12 has to do with sound. So it says sound, the transmission of the vibration of molecules to the air. So when we're done with our notes, we'll do a demonstration and actually see this. So sound waves are longitudinal waves. They need a medium to travel through. So sound has to travel through something. Now we know sound travels through air because I'm speaking to you right now, and the sound that's coming out of my mouth is going through the air, and then it's reaching your ears. But sound doesn't just travel through gases. Sound can travel through a solid, a liquid, or a gas. So sound can travel through a solid, like the desk. Solid sound can travel through a liquid, like water or any other liquid, but it does need a medium to travel through. So what that means is it cannot travel through somewhere where there is no matter, which would be space. So it cannot travel through the vacuum of space. If the moon exploded, the moon's pretty big. If it exploded, do you think we'd be able to see it? Well, the light waves emanating from the explosion we'd be able to see, but we wouldn't be able to hear it because between the moon and us there's space, and the sound waves wouldn't have a chance to reach us. The speed of sound depends on the medium it passes through. It also depends on the temperature and humidity. So those of you who are in band probably see this all the time. Someone takes like the big drum and they hit it, and if they're on the other end of the football field, there's actually a delay from when they actually physically hit it and you hear it, because it takes time for sound to travel through air. And sound isn't that fast. It's about 343 meters per second. But again, things in the air like the temperature, whether it's hot or cold, the humidity, because when it's humid there's more water vapor in the air, that can all change the speed of sound. Even if it's going through a solid, the type of solid, because solids have different physical properties, they have different densities, and that can also influence the speed of sound. So the velocity of sound increases as the temperature increases. Now we had learned in the earlier chapter about longitudinal waves, and we learned that longitudinal waves are a series of compressions and rarefactions. And sometimes we can help us see this with a device called an oscilloscope. So now when we talk about sound waves, we're going to talk about certain parameters. So first of all, one is the pitch. And when we do our lab using the theremin, which we already looked at, but we're actually all going to get to play with that, we're going to see that when we move the hand up and down, we're actually changing the pitch on the theremin. So the pitch is the highness or lowness of a sound. Now the loudness depends on the amplitude, which actually also depends on the energy. The more energy you put into a wave, the greater the amplitude and the louder it's going to sound. Now today I'm going to explain something called the Doppler effect. Now the Doppler effect is a phenomena that you experience all the time, but maybe you never really even thought about it. Now some of you, when you think of the word Doppler, you think of like Doppler weather. So Doppler has to do with the change in frequency of waves of a moving source, or also with a stationary source and you're moving. So we're going to look at these two examples. So here's the first example. Okay. So here is a police car that's moving. Okay. Now, if the police car was stationary, so let's say the police car was stationary. It's kind of what the police car looked like. And its siren was going off. If it was standing still, the sound waves are going to be coming out of the police car, and because the police car is standing still, the distance in between all the sound waves are going to be the same, right? But let's say the police car has its siren on and it's moving. Because the police car is moving in this direction, the police car is catching up with the waves that are coming out of the siren. So if this is the way the police car is moving, in the front of the car, the waves are getting closer together. Okay? But as the police car is moving this way, because it's moving, these waves are getting farther apart. So because these waves are closer together, they have a smaller wavelength, but they have a higher frequency. Because they're spread out here, they have a longer wavelength, which gives us a lower frequency. Okay? Now, if you're standing here and you're stationary, as the car approaches you, because these sound waves are closer together, again, it sounds like a higher pitch. If you're over here, you're going to hear a lower, it's going to sound lower. There can also be where you're stationary and it's coming towards you, and I'm actually going to have you listen to something to hear the difference. Now, another effect of sound waves, and I'll just draw a picture because it'll help to explain it. So let's say I have an airplane. The airplane is sitting on the runway at the airport. Okay? This is a jet plane. So the plane turns on its engines, and the engines are loud. Okay? So now what's happening is the sound waves are coming out of the engine. So they're the same distance apart. Okay? That's what the sound waves look like. So now the plane takes off, and it's going really fast. And what's happening is the plane is approaching the speed of sound. So now the plane is going almost as fast as the sound waves that are coming out of its engines. So what's happening is that the sound waves are crowding together in the front of the plane like this. Okay? Because the sound coming out of the engines is almost as fast as how fast the plane is going. And then here they're spreading apart. Now the plane is going the speed of sound. When the plane is going the same speed as the sound waves that are coming out of its engine, what happens is all of these sound waves bunch up. Is there something in between these sound waves? Sure there is. Doesn't a plane fly through air? So air consists of molecules. So all these molecules become compressed. And what happens when something gets pressed? It's under great pressure. So this forms something called a pressure barrier. Okay? All these compressed air molecules are squished in between these sound waves. And this pressure barrier is something called the sound barrier. Okay? Now what happens is, and they didn't realize this till the 1940s, is this plane can actually go faster than the speed of sound. And when it goes through this pressure barrier, it makes a noise, and that's called a sonic boom. Okay? When it goes through that sound barrier. Okay? So this helps to visualize that a little bit. Okay? Now, going back to the note. So this talks about shock waves and sonic booms, and this shows you a picture, but I think my picture was a little bit better, even though I drew it. All right. And we're going to see all of this. I just want to go over the notes. So now we're going to talk about sound intensity. So the intensity of the sound. So intensity has to do with the rate. So rate is always a measure. So this is the rate at which the energy flows through a unit area. So the intensity is equal to the power divided by 4 pi times the distance from the source squared. So this is one of the equations, if not the only equation that we're going to be doing in Chapter 12 is sound intensity. So here's an example. What is the intensity of the sound waves produced by a trumpet at a distance of 3.2 meters when the power output of the trumpet is 0.20 watts? Okay. So again, we're going to write down our given. So this is what we're given, the power and the distance. We want to find the intensity. We write our basic equation. We substitute in our values and solve. And we notice that here we have a new unit. In our unit here, when we're measuring sound, the power is Webers. Now, a device that we'll look at sound meters measures the volume of sound in something called decibels. So you might hear this in everyday life, something referring to something as far as decibels. So decibels refers to the volume, which is the loudness of a sound. So just to give you a frame of reference, normal talking is 65 decibels. A whisper is 40 decibels. Rustling of leaves, 50. Now what happens is that when it gets to be too loud, has anyone ever had the stereo on their car on, and then you went out, and then you came back on and turned your car on, and it was like really, really loud and it hurt your ears? So it could have been painful, because when sound is too loud, it can cause pain. So this says right here, 120 decibels is the lower limit of pain, but you see that a jet engine is 160 decibels. So whenever you go on an airplane and you look out the window and you look at those guys that are directing the planes where to go, they have ear protection on. And they don't just have on one source of ear protection. You see them with things over their ears, but they also have earplugs underneath them. They actually have double ear protection. Because first of all, this can be painful. Second of all, it could cause permanent or temporary hearing loss. When you are exposed to certain sounds that are loud, it can cause temporary hearing loss or even permanent hearing loss. So this is just, again, a chart showing you the different levels of sound, just to get and see what relative everything is. Now we have something called infrasonic waves. So these are frequencies below 20 hertz. So we can't hear these. Then there's ultrasonic waves. These are sound waves with frequencies above 20,000 hertz, which we can't hear also. Now, what we can hear as humans is different what other species can hear. I'm sure some of you, if you haven't seen one in person, you've seen it on TV, a dog whistle. So dog whistles, usually the frequency is so high that we can't hear it, but dogs can hear it. And different types of animals can hear different frequencies. So dolphins and bats, they can hear frequencies greater than 100,000 hertz. Now, as you get older, what happens is a lot of times your hearing changes. So some of you, maybe your grandparents have hearing aids, or you have to talk loud, or they can't hear certain frequencies. And that's because hearing has to do with anatomy. So those of you who took or in anatomy, those of you in the medical academy learned all about little bones that vibrate in our ear. And you've also learned about how within our ear that the tissue isn't as tight, and we don't hear as well as we get older. So also the speed of sound changes in different materials. So in a vacuum it doesn't go because there's no medium. In air it's about 340 meters per second. In water it's about 1,460. So we see speed travels a lot faster in water. In copper, 3,560, and then aluminum. So we see how it changes significantly. So I need to do a couple of demonstrations, and this is just a very quick introduction to sound.